Hello, and welcome to section 4.5 on L'Hôpital's rule. In this section, we make an observation using derivatives, which allows us to obtain a new limit technique. As we use the differentiation rules, which we learned in chapter 3, it's important to remember that all of calculus rests on the concept of the limit. After all, derivatives were originally defined in terms of limits, and the derivative rules, which were developed in chapter 3, are just useful shortcuts. Recall that when we compute a limit, such as this one, the first thing we try is to plug in the limiting value of our independent variable. This becomes more difficult when direct substitution doesn't give us a concrete number. In some cases, however, we can still interpret the value of the limit using the information gained from direct substitution. In this example, we see that plugging in gives us 1 over 0. We know that this limit never exists because we can never divide a non-zero constant by 0. Even though 1 over 0 is not a number, there is no ambiguity in this case. The limit is unbounded, heading towards an infinity. Therefore, we call this a determinate form. Be careful with this new notation. It isn't that 1 over 0 equals infinity. It's that if a quotient has a numerator which has a constant limit, and the denominator has a 0 limit, then the limit of the quotient has the determinate form 1 over 0, which means that the limit tends towards an infinity. Another example of a determinate form is 1 over infinity, which we know always gives the limit value of 0. Where things become really tricky is an example like this. When we use direct substitution, we get the form 0 over 0. It's not clear how we should interpret 0 over 0. In general, we cannot divide by 0, so we'd like to say the limit does not exist. However, we also know that any expression divided by itself is equal to 1. Because we have no good reason to pick one of these options over the other, we say that 0 over 0 is an indeterminate form. That is to say, the limit cannot be determined from the given information. Here's an example of another limit which results in an indeterminate form. When we attempt to evaluate the limit, we get the form 0 raised to the 0. Again, there is ambiguity in this form. 0 raised to any power is equal to 0, but anything raised to the power 0 is equal to 1. Again, we stress that strictly speaking, 0 to the 0 is not a number. It is the form that this limit takes. In particular, it is a form which does not give enough information to determine the value of the limit. Going back to the first example we saw, how do we solve this limit? In chapter 2, we use various algebraic techniques to eliminate the ambiguity of an indeterminate form. Do any of these apply here? Can we multiply by the conjugate or factor? Simplify any compound fractions? No, it doesn't seem like we have any useful methods for simplifying this expression. This is where L'Hôpital's rule comes in. Let's look at the graphs of the two functions which make up our quotient and see if we can get a geometric intuition for how we might evaluate this limit. We know that in computing the limit as x goes to 0, we only need to consider values of x very close to 0. Recall from section 3.9 that the curve and its tangent line at x equals a are almost identical as long as we're near a. If we zoom in enough, we will find a scale where f of x and g of x look very much like their tangent lines. Therefore, let's assume that we can replace f of x and g of x with the equations of their tangent lines in our limit expression. The resulting equation that we get is that the limit as x goes to 0 of f over g equals the limit as x goes to 0 of f prime over g prime. If we start with a limit which has the indeterminate form 0 over 0, we can always use this reasoning to compute the limit. This fact is called L'Hôpital's rule. Now that we have this tool at our disposal, let's return to the limit which stumped us earlier. Since this limit has the indeterminate form 0 over 0, we can replace the top function f of x with its derivative f prime of x, and the bottom function g of x with its derivative g prime of x. Now, evaluating the resulting limit, we get 3 over 1, which equals 3. L'Hôpital's rule tells us that this is also the value of the limit we had to begin with. Thus, the limit as x goes to 0 of e to the 3x minus 1 over sine of x equals 3. There are other indeterminate forms as well, some of which we've seen and some of which we haven't. Each of these cannot be determined unambiguously, just like 0 over 0. Since L'Hopital's rule only applies to limits of the form 0 over 0 or infinity over infinity, we can't just take the derivative of whichever expression we have and reevaluate the limit. In class, we'll discuss ways of manipulating each indeterminate form to get it into the form 0 over 0 or infinity over infinity so that we can apply L'Hopital's rule.